Hello again, everyone. I wanted to go through a little bit or look at a particular problem once again from chapter 28 from the Katz book, first edition. That problem from chapter 28 from the Katz book, first edition, will be problem 82. We already did it. It got done. Perhaps in a more efficient manner it could have been done when I did it, but we discussed all the matters that we wanted to discuss, and I believe even more than that. So hopefully that's worthwhile for everyone if you want to look at it. Let's look at it again and draw the same conclusion and maybe just hopefully streamline this a little bit, a little more concise presentation of it, and then talk about some do's and don'ts. I mean, there was a lot I talked about last time regarding this particular problem in another film. But now I'd like to say much the same things, but then something else that I think it's of interest. I guess a particular angle on this whole matter that we might find of interest. So let's talk about it a little bit. For the record, let's just read it again. It's on page, Katz book, first edition, chapter 28, page 894. Page 894, problem 82. It says, a conducting material with resistivity ρ is shaped into a wire of length small l with a tapered cross-section that decreases from radius r1 on the left end to radius r2 on the right end. If the current density in the wire is a constant, as a function of the horizontal distance x along the wire, what is the resistance of this tapered wire? So the current density of the wire is going to be a constant as a function of the horizontal distance x along the wire. What is the resistance of the tapered wire? So they tell us a few things. We worry about some things, perhaps worry about others, but others we don't have to worry about at all. So we're talking about the current density, and the way they had spoken about that, it's not really going to be an issue for this thing. Because the current density is a constant as a function of the horizontal distance x along the wire. So let's take a look at it. Well, we know that for a constant here, there's a number of ways we can look at it, I guess you could say. The resistance is directly proportional to, for a given resistivity, it's directly proportional to the length. The longer the wire under consideration, the more resistance is going to be offered to the flow of electricity. It makes sense. It's got to get through a lot more wire than it would maybe in another scenario. And the cross-sectional area, if the cross-sectional area is big, it's going to be easy for it to get through. Okay? So that's that's the bread and butter here. And this works for any sort of length and for any sort of cross-section along the length, where the cross-sectional area along the length is constant no matter where you take it. Yeah, no matter where you take it, no matter where you measure it, the cross-sectional area is going to be a constant in a lot of circumstances. Well, it's certainly not a constant here. The cross-sectional area here gets smaller and smaller and smaller until it goes to here. It does behave. The radius changes in a linear fashion, which is of interest as well. I mean, remember, you look at what's the equation of a line? Y equals mx plus b. Well, what could I do here? I could talk about the radius, what it is a function of something, and you could say, well, you know what, it's a decreasing radius. Well, what is the slope, I guess you could say? Well, the radius drops from a radius of R1 down to a radius of R2. So R2 R2 is small, R1 is big, so this is going to be a negative slope. Yeah, it's getting smaller. So R2 is small, R1 is big. Negative slope, it keeps getting smaller. Over L, that's the slope of this thing. And if you start at x, I mean, so you could for any and x is right here. The x-axis goes right through. I almost don't want to draw more, guys, than what I have up here. But the x-axis starts right here, right at the center of this circle is where the x-axis starts for us. It's x equals 0, and then it goes that way. So if that's the case, for x equals 0, here's the slope, x equals 0. 0 times this is all 0, but I got to get an R2, or rather an R1. Does this work? Yeah, it works. Put a 0 right here. 0 in for x. See, you got two places here. You got this right here, where x equals 0, and you got this right here, at least for now, where x equals small l. I could probably switch this thing. I could, flip this thing, do a 180 with it, and start from the small going to the big, and maybe it's a little more intuitive. You're going to get the same answer. We can look at that as well. Well, does it work from the get-go? I mean, do you get a radius of R1? Does R become R1 when x is equal to 0? That's 0. Add R1 to it, you got the R1. Okay. A little more challenging is, do you get an R2 if x equals L? Put an L right here. Put an L right here. L and L cancel. R2 minus R1 plus R1 is R2. Yeah, it works out. It works out. And it's generally going to work out. Everything we want in there. This thing tapers down, and as it goes, the radius goes from the big one, R1, and gets smaller and smaller and smaller until it gets to R2, the smallest radius, when you're doing this. So absolutely, believable. And it's of this form. We can make it look like this. Yeah, we said that too. Okay, let's see how we can do it. This thing's it's varying too much. This only works if the cross-sectional area is a constant throughout the length L. Well, this cross-sectional area continuously changes throughout the length L. Certainly not a constant. Now let's evaluate it and see. It only works when the area, cross-sectional area, is a constant for a given length, and then you can work it that way. Well, I can't do that here, but I tell you what, I can add all the resistances, because in bits and pieces, you guys, this thing's got a resistance. So does this. So does, and I should have maybe, give them a little circular look to. I mean, all these cross sections have resistances, and I guess since they're all in series, I add the resistors together. When resistors are in series, they add up to give you the grand total resistance. Well, each one of them is going to be a different resistance because you got something different going on there. And we could talk about it, there's a whole lot of other stuff we can say as well. But so if that's the case, you guys, the real big move that runs this, and I have this in my notes. In one part I neglected to put, let me just show you, and we can just talk about it. DR, just show you, there is a place in the notes where, yeah, absolutely, I have this in the notes. And then there's a place in the notes where I'm actually about to do the integral. I neglected to put the differential notation here, and I just had R equals this. Well, yeah, this does equal some kind of resistance, but it's a differential resistance. So this, it's in the notes fine, so you can see what's going on there. Just watch out for that. There should be a DR somewhere else later on. But like I said, if you walk through the proof of how we did it, you should not have a problem. It's pretty straightforward. But this is what's going to do it. You're basically going to take in the limit very, very many resistors, each one of them with a very, very small resistance, and each one of these green things is the small resistor, small resistor, small resistor, small resistor. They go toward infinity, the less broad the dx is that we're talking about, if you take it in the limit. Obviously, clearly a calculus problem. You're adding all those resistors together, they're in series with one another. If they're in series with one another, they'll give you the grand total resistance. So what you have is, you got this right here, and that's huge. That's huge. You're basically, to find the resistance, you guys, you're basically doing this. That resistor is going to be the sum of all of those infinitesimal ones. If there's a finite number of them, I guess I could add a finite number. If there isn't, I got to do an integral. And that's going to be, well, what is dr? It's rho dx over a. Okay. Rho's a constant. Rho's a constant, and let's just talk about A. A is going to be what you can say for the area. Well, there's cross-sectional slices there. Each cross-sectional slice is a circle. Find the area, find a general formula for the area of the circle as we proceed as a function of x. And that's really the big thing. That's a big, big move to make, guys. But once you make it, you're okay. So much to say. Let me just, let me try to be brief because, I think it's just better to be brief sometimes if we can do it. The last time we went into this in some pretty excruciating detail. Now like I said, we have this. Let's see what we can talk about as we have this up here. You got it looking like this. Just find A. Once you find some kind of a formula for A, I think you're in business. So that's the hardest part, guys, of the whole thing. What we got is rho dx. Where's the A? I'm just saying. I'm repeating this, guys. I'm repeating that format, that look. Well, how about pi r squared? If r is looking like this, let me write it like that. In my notes, I wrote it in a little different order, but that shouldn't matter. That shouldn't matter. I think we're in good shape. So there's the A. This whole thing is the A at the end of the story here, whatever it's going to be. And let's see what it is. Pi r squared. Okay. Without further ado, let's square it as is, and let's go. What's the r? It's pi r squared. There's your r. Certainly there's your r. So is this. It's the same thing, and that's what you need. This makes it a function of x. This doesn't tell me enough. This doesn't tell me enough. It tells me the structure of what I'm looking for. Certainly. All right, so try to darken that, and it's less visible, I think. Try one more time. Just leave it alone, and we got that. Okay. We've got that's it. This is the key to the whole thing, you guys. That thing right there is the whole thing. I mean, this is r, which equals all that. Pi r squared is pi r squared, which is pi times all that quantity squared. That's the area under the bottom right here. Okay. I'll write it again, make it a little more legible. I think it's going to be okay for you guys. Typically when I look at it, it comes out okay. But that's pretty important stuff. Pretty important stuff in that regard. So when we do this, yeah, I mean, the rest is going to get done. So let's see how we want to do this. I've already kind of discussed this in the past. How it looks, how we set it up. But we just kind of just said it. Let's put it together. Let's put it together. We're looking at this right here. So what you're going to say is, at the end of the day, the r is going to be the integral from 0 to L dr. It's going to be the integral from 0 to L rho dx as we said here, guys. R2 is the small one. Here's your slope. Here's your x. Pi gets all of this. R1's yeah, it's going to be all that. Pull a rho out of there. Pull a pi out of there. They're constants. And you've got dx equals r sub 2 minus r1 over L times x plus r1 right here. You're basically, the y equals mx plus b is r equals mx plus b. The m is r2 minus r1 over L. The b is r1. And that's where it's all going to happen. It's all going to happen with that, you guys. This is the end of the story, if you can get it to work. Now, there's a lot of ways to do this. We can look up in an integral table what we have to do here. You know, they've proposed some stuff, and like I said, some of it you can go, it's kind of a long shot sometimes to go hit and miss and take some good guesses on it. But we can you certainly can do it, you certainly can try it, and we can certainly verify in a very logical manner what is, you know, what is the integral? What is supposed to be? What are the antiderivatives supposed to be? So, the way I drew that leaves a little bit to be desired, but there it is. I mean, so it's looking something like that, you guys. How are you going to make it work? Well, in the problem itself, R1 is a constant. It happens to be in this problem itself, R1 is a constant. It is the large radius. R2 is also a constant. So R1 is a constant. It is the large radius. R2 is a constant. It is the small radius. Small radius minus large radius is going to be a negative number, but it's a constant. R2 and R1 are constants. L is a constant. X is the only variable here. These two are constants, so I pulled it out of there. So this is really it, guys. I mean, I emphasized that last time, but let's do it again, hopefully a little more smoothly for you guys, maybe a little more concise. And maybe there's some commentary here that deserves our attention, or some matters of interest that deserve our attention, I guess you could say. So we can look at this, you guys. We're saying that. Tell you what, let's not worry about the constant out here. That's not a big deal. I mean, we'll worry about it when we have to worry about it. It definitely does play a role in our conclusions here and in what we have to say. But right now, look at everything, and everybody's a constant except for that x right here. A constant times x plus a constant. That whole quantity squared, dx of, integral from one place to another, integral somewhere of dx over a constant times x plus a constant, whatever's down there squared. So constant here, there's an integral between two limits. All right, the integral of dx over this quantity, this entire quantity, a constant times x plus another constant, that whole quantity squared on the bottom. Do that integral. What's going on? Well, they mention that in general, I mean, and again, it's hard to come up with this stuff, but they come up with it, and we can believe it because the conclusion's pretty good when it gets done. If you're doing an integral of, and oftentimes they use du's when it just seems to be the standard they oftentimes use. It's not a big deal. Look at the actual situation, I guess you could say. Some AU plus B on the bottom, that quantity squared, if you integrate that, not going to worry about the limits or anything like that. Let's just get an antiderivative. Turns out the antiderivative is, now remember now, A and B are constants. Use the variable. A and B are constants. Got negative A over B times 1 over the quantity AU plus B. That's the antiderivative. Really? Yeah, sure it is. If you were to take this quantity and get its, if you were to take the derivative of negative 1 over A how would you do it? It's the same as getting the derivative of 1 over AU plus B to the negative 1. All right, go ahead. Yeah, I guess you could say that. There's no I guess I could say it. You actually can say it. This thing right here, 1 over this quantity, is this quantity to the negative 1. Do the derivative. The derivative with respect to u of this quantity is going to be negative 1 comes out in front. So negative 1 times negative 1 over A. Subtract 1 from the negative 1 here. True. True. Let's have a look here just to be sure on this. Okay, do that. Yeah, and then by the chain rule, the derivative of AU plus B with respect to U. That's an A. What's going on here? Negative times negative is positive. Forgive me, more than that actually. Negative 1 times negative 1 is positive 1. A and A cancel. That's just positive 1. And at the end of the day, you got the quantity AU plus B to the negative 2. What is that? That's what's underneath here. 1 over AU plus B to the 2. So when they're saying something like this, you guys, if you're going to look at this and actually do it, you're saying, okay, well, they're making that claim here, so let's kind of just, you saw what I just did. So let's kind of give it yet another look. Give ourselves a little more room, guys. I'm always a little apprehensive to go on the edge of the boards here. Don't know how the visual quality is all the time, but it's been pretty decent, so I think we should be okay. But, you know, you never know. We're making that claim. Well, I don't know. If I get the derivative of this, I should get the thing on the bottom here. You got to remember, this is simply, you know, it's simply 1 over. You know, it's simply, you know, I don't know how you want to say it. Usually just put the du on there, but just to be really explicit about it, you got AU plus 1 over all right, put the u like that. Is that the same as this? Same as that? Yes. All the above. Not the greatest written depiction of it, but that's the claim. Is it true? I mean, verify it again. Are you going to get this? I mean, or are you going to get this? Well, if you're going to get this, that means if you're going to get this, and you are going to get this, if you're going to get this, then the derivative of this will give you what's underneath here. 1 over, or at least it will give you 1 over the quantity AU plus B squared, which is this. They're all the same, which is the same as that. Can you get to that? Yeah, pretty easily, actually. Pretty easily. You're basically going, when you're taking this, you're going d of and you know that this right here, we're going to call it, just for the sake of the mathematics that we know, that we've been able to prove in the past, in different courses or on our own, they're asking this. I'm asking you, is this going to work? Is this thing right here, which is the integral, which we're claiming is the integral, and indeed is the integral, is its derivative with respect to u going to work? Yeah. Because that right there equals the derivative, this whole thing right here, as it is going to be the derivative of this quantity right here treating this as a variable, the whole thing as a variable, times that whole thing absolutely. You're treating this as one big X. Well, then it's a negative 1 over A constant. The 1 big X to the negative 1. What's the derivative of 1 big X? What's the derivative of 1 big X to the negative 1 with respect to 1 big X. This is just 1 big X, this is 1 big X. What is the derivative of what is the derivative of the product, negative 1 over A, with the multiplicative inverse of 1 big X with respect to 1 big X? The derivative of all this, which is negative 1A times the quantity AU plus B to the negative 1, the derivative of it with respect to AU plus B. So it's negative 1 over A times 1 big X to the negative 1 with respect to 1 big X. Well, that just becomes just an X right here. The negative 1 comes out, the negative 1 comes out of there, and you subtract 1 from the negative 1, you get negative 2, and you got AU plus B to the negative 2 times negative 1 times negative 1 over A. So this part right here the negative 1 comes out of there. You've got negative 1 over A. The quantity AU plus B to the negative 1, the derivative of it with respect to AU plus B is the quantity that is that big AU plus B we were talking about with respect to AU plus B to the negative 1, the derivative of it with respect to AU plus B is, wow, subtract 1 from it, take the negative 1 in front, subtract 1 from it, you get this. So this is what you got here. Here, this with respect to U is just A. It's a little messy the way I don't want to put it over. You can put them over 1, not put it over 1. Stuff gets, so when you actually finally do it, that's an A. Well, great. Is it going to give me what I want? Yeah, it sure is, guys. I mean, it's going to be negative 1 times negative 1. That's positive 1. The A and the A, that's positive 1. So it's just positive 1 times this. At the end of the day, guys, this is AU plus B to the negative 2. That's going to be 1 over AU plus B to the 2. Absolutely. There's your derivative. If you take the derivative of this, take the derivative of all of this, take the derivative of all of this, you get here. That means this is the antiderivative of this thing being integrated. You integrate this thing, you will get as an answer, to a large degree, the antiderivative. If you integrate something, you'll get its antiderivative. This is its antiderivative. How do I know that? When I take the derivative of this, I get that, which is the same as this. Which is the same as this. So that's good. I mean, so, okay. Well, that's it. I mean, that kind of, at the end of the day, guys, we're going to use this right here to solve what's going on over here and get the answer we were talking about. Okay, everything's believable. Okay, so be careful. And I got, like I said, the last time we've done it, I got a little careless with that. I think the problem was essentially solved, and I just ignored that I ignored that the problem was actually almost solved. and went down a different path because I didn't see something that was there. So let's make sure we see everything that we have to see. You got it here, guys. I think we know what it is. I mean, it's going to be rho over pi and all of that, which is going to be, this is the A, quantity R2 minus R1 over L. So negative of that, so it's going to be negative the reciprocal, which is going to be R2 minus R1. It's easy with these negatives to start to have some kind of an issue, guys. You're going to have that right there. That's a constant. This is a constant, no problem. The rest is, yeah, basically right in front of us. What you're looking at is 1 over here's your A, here's A, here's U, yeah, I mean, here it is. I'll put them like this. Kind of draw a big picture here, I guess. Yeah, that's it. What do we think? We know a lot. I mean, so what we have here is it's going to be evaluated from 0 to L. And let's just, I mean, like I said, let's just start going for it. This is a constant right here. So the rho, you know, the negative L and the quantity R2 over R, the negative L and the quantity R2 minus R1, that's a constant. Let's pull them out of there. Let's see what we can do, guys. You see what it looks like. You've got the record of it. So we'll come back to some of this, I guess. We'll see what we can say. Okay, we had what it had to be. So let's see what we can do here, guys. Go this way. Go to the left a little bit with the equation. The equation is an equation, no matter what direction I'm going to go with it. It's going to be negative. What's going on here? Don't let that negative scare you. You know, there's a lot that can take place. Just deal with it. I mean, the R2 is smaller than the R1. R2 is smaller than the R1. That's a negative. All of these are positive. All of these are positive numbers. The minus sign makes this quantity a negative, and this negative makes this quantity a negative. They're all positive numbers otherwise. small minus big, negative answer, and here's negative. Negative divided by negative is positive. Yeah, it can get a little messy. You've got the, start at the L. Start at the L. Put an L right here. The L's cancel. You got R2 minus R1 plus R1. That's R2. That's R2 on the bottom. R2 is small. If it's small, its reciprocal is a big answer. It's going to be a big positive answer. Put a 0 right here. 0, that's out of there. You got an R1. R1 is big. Yeah, I know, but 1 over big is small. 1 over small is big. Big minus small, positive number. Negative divided by negative, because it's small minus big, negative answer. Negative divided by negative is positive. This is a small number. Look at it. It's not a big radius. This is a big number, means big radius. 1 over small is kind of big. 1 over big is kind of small. Kind of big minus kind of small is definitely positive. It's a positive answer. This is a positive answer at the end of the day. So that's kind of, I just wanted to go through that with you guys again. I mean, because like I said, the last time, even one little careless mistake, and what I made, how little was it? Well, it took a lot longer to do the problem. So it's a careless mistake. It can be fixed. Sure, it can be fixed. We fixed it, but it took forever. Here it's a little more straightforward to look at. What are we talking about? What is this? Let's go up here. This is negative rho over L over pi R2 minus R1. Let's see what happens. We said this is going to be a positive answer. So let's see how it works. Tell you what I'm going to do. Multiply this quantity by a special one called R1. Multiply this quantity right here by a special, ignore this right now. We'll take care of that at the end. We'll take care of the subtraction. Multiply this quantity, 1 over R2, by a special one called R1 over R1. It's R1 over R1, R2. Here, here's the minus. Okay, we'll deal with it. Multiply this quantity by a special one called R2 over R2. Special one was R2 over R2. We got this. Multiply this by a special one. Don't deal with this right now. We're not dealing with it. Multiply that quantity by a special one called R2 over R2. You get this. Multiply this quantity by a special one called R1 over R1. Don't deal with this yet. R1 over R1, and we get what? This. Absolutely. What's going on here? Well, what we get is negative rho L yeah, that's small, that's big. Both positive. Everything's positive in here. The subtractions and the negatives that we're throwing in front are making things negative. But rho L, pi, R2, R1, they're all positive. The order here is that's bigger than that. This is bigger than that. So that minus this. This is bigger than that. So that minus this can be a negative number. Wait a minute. Take the tops. R1 minus R2. Wait a minute. Looks a lot like that. Only opposite sign. Yeah. Magnitude's identical, only opposite signs. So when you do this, I don't care if the negative's on the bottom or on the top. I'm just saying they've got opposite signs. It's going to be a negative. Yeah, it said everybody's positive except for where there's a negative. What's a negative 1 times a negative row? It's a positive row. Row L. Yeah. Pi. R1, R2. You're done. That's how easy it was last time. Like I said, I made a careless mistake. I thought there was more negatives there than were actually there, and made some decisions I should not have made. That's it. And there's a variety of ways. I mean, at the end of the day, how we wrote the thing doesn't really matter. I mean, that's not the big. The big thing is, I think I have it as. I mean, I can't remember how actually. There's another way. I mean, it's not a really big deal, guys. I mean, you got it all. I mean, you got this rho over pi, and then you got L over R1, R2. Correct. Yeah, and we said how that played out. I mean, we said that, and like I said, at the end of all that, yeah, there's different, the way I wrote it, I think it's the way the textbook wrote it in their T as well. You got this right here, guys. That's fine. I told everyone, I mean, it's a pretty fascinating conclusion. When we look at it carefully, the conclusion's pretty fascinating. Remember, they're kind of saying, no, there's no kind of about it. They are saying if it's constant, you're talking about something like this. True. Even though there's nothing really constant going on here, we had to use calculus to get it. We came up with a conclusion wait a minute, that right there is the area of an ellipse. If that area of the ellipse is constantly found without variation across the whole length L, if it's a kind of cylinder, that it's a cylinder that has cross-sectional area equal to an ellipse's area, and that ellipse's area is a constant number. It's a constant value, I guess you could say. If there's no variance in the elliptical cross sections, each elliptical cross section across the length L will always invariably have this area, pi R1, R2. So if somehow this was designed as, like I said, it was like this, not like that, and it was an ellipse from start to finish, and you could, like I said, make it as big as this. I mean, make it every bit as long as this. Small l in length, you'd have the semi-major axis of length R1, the going upward. Let's just look upward. I get up here, looking at this, just upward like this. Throughout the process, if the thing was like this, like that, hey, it looks like too much. Yeah, but it's narrowed somewhere else, So if the semi-major axis was R1, and then coming out at us was this length, R2, it would look like an ellipse. If you look straight at it, you'd be looking at this. Here's your R1. Hope you guys can see this okay. Let me draw that a little bit bigger. And here's the R2. So if you had it, there's the R1, and there's the R2, and the area is pi R1, R2. And if it stayed, if the cross-section, every cross-section you cut was an ellipse of the exact same size as every other ellipse that's within that length of L. It's a constant, the area is a constant cross-sectional area. It's a constant value for the area of the cross-section over that length of L. And that area were pi R1, R2. This would be the cross-section. Here's how it would look. You could also say, here's how it would look this way. It'd be up here. It's like, wow, that's awfully big that way. Yeah, but it's interesting how that works. But on the other end of it, it's on the going up this way. Yeah, it's as big as R1. Coming out this way, it comes out to the minimum, which is R2, the minimum radius that could happen out this way, and then it'd come that way. Now somebody might ask, well, wait a minute. That means the volume of both of those propositions must be the same. At the very least, the average area must be the same. There's got to be an average area cut right here, and I guess it would have to be pi R1, R2. Something I wanted to talk to you about. Let's just kind of look at it. Pretty fascinating stuff, guys. Well, yeah, you'd think that'd be the case. Yeah, remember though, this is kind of the big thing. We don't really care about the area, quote unquote, on the top of the numerator. We care about the area in the denominator. So maybe there's, you think, well, there's got to be a connection here. If we can show one example where there's not a connection, then it's generally not true. It might be true sometimes. Who's to say? Our big conclusion right now is we want to say that we're hoping there's some kind of general conclusion we can draw. Yeah, I think there is, but it's not the conclusion that we want to draw. You're not going to get an average area in both cross sections that are going to be equal to one another in general. Perhaps there is here. I don't know. Let's look at it. But if we can show one example where that's not the case, then then you cannot say that it's generally the case. It's generally not true. It may be true, it may not be. That's another issue in its own right to be explored in some other manner. But can we at least show that it's not going to be what we might think it's going to be? Well, I don't know. The volume of that cylindrical of that elliptical cylinder, the volume of that elliptical cylinder is pi R1 R2 times L. True. That's its volume. What would be the average area? That's the mean value theorem. If you do calculus on the matter, that's really where the mean value theorem comes in. You integrate, you find out what the volume is, and then you divide by the length over which you divide by the length of the interval over which the integration was taking place, and that'll give you an average area. It's an extremely useful formula. We've seen that in Taylor's formula. We talk about it. We've seen this in we've seen this in a lot of places. You'll see it's a very, very important formula to conceptualize a lot of what's going on. Very important formula, the mean value theorem. So what are you trying to say here? Well, isn't V equals some average area times L? Okay. Then V over L is going to be equal to this over L is going to be equal to, well, I'm not saying anything too profound here, guys. These cancel. We already knew. That'll work. That'll work. Okay, we know something mathematically speaking. Sure, okay, that's for the other. Is it going to be the same answer as that guy. You know, is it going to be the same answer? That's the thing. There's a lot you could say, I guess. I mean, we could do this a whole bunch of ways. I mean, some crazy math you could do here. You could, don't know how much time we got, but let me propose a couple things here. You could kind of take this guy and extend him all the way down to a point, and then you got the volume of a cone. Get the volume of the entire cone, and then subtract this imaginary volume that you constructed here, and you'll get that. That'll work. You got to wheel and deal a little bit with that. You got, because you don't know how long the cone's length is, and you don't know how long the new thing is. For this thing to go down to 0, that's another thing, right? That's its own fascinating thing, I guess you could say. You could say, I don't know that I'm going to go down that path, guys. I'm not sure how much time we got to go down that path. But you saw me when I said that y was equal to mx plus b. We kind of played some games with that. And we said, okay, this thing's, as you go from x equals 0 to x equals L and onward, as this is happening, you know, if that's happening, we said there's kind of like a fall down here. Well, we said the R2 is the small one, and the R1's the big one. Okay, remember this. It's a negative slope. R2 small one, R1 big one. L, X, R1. Yeah. If it looks familiar, it should. We just did it, right? And this right here, we said was M on the whole process. So where could you get the radius to be equal to 0? You know what I'm saying? That's kind of where you could kind of say, well, how long? I know at L it's at L it's at R2, right? You put L right here. L and L cancel. R1 plus R2 minus R1 is R2. Okay, put 0 here. You got R1. So you go from R1 to R2. This does it. Man, how would you get it? It goes all the way down to the cone goes to a point. A point, R is 0. If R is equal to 0, put a 0 right here. 0 equals all this. Get this thing over on the other side, and you end up getting negative equals R1. Take the negative throughout. It's going to be the big minus the small over L times X equals R1. It's going to work just fine, guys. Multiply by the reciprocal of this. Multiply by the reciprocal of this on each side. And you end up getting R1 over, that's big, that's small, positive answer. That's positive answer. Okay, it's a positive answer. And it's longer than L. Why is that? Because this right here is smaller. It's a positive answer, but it's smaller than R1. A big divided by a small is going to be a ratio bigger than 1. Yeah, we know it's going to be longer. It's going to be that far away. It's going to be all the way to that distance. So that's the distance to get all the way to 0. That's rather interesting. Again, this is the thing we're trying to see a connection here, and I don't think we're going to see it, but it's there. So what are you going to do? Well, how long is that distance? There's a number of ways you can go here. If I divide by this with what's going on here, oh yeah, it works. Yeah, I know. I better be getting the exact same number though. Here, I better be getting the exact same answer. Pi R1 R2. Well, this is the whole long distance. minus the small one. What's the small one? Well, you could play, and I'll do an integral too, and we should get the right answer. They have derived through calculus, everyone, they have derived that it's 1/3 pi r squared L, or height, right? The volume of a cone is 1/3 pi r squared h. Perhaps. Perhaps. I mean, it is. I mean, we'll actually do it to actually find out. But if this is the case, why don't we just get like? Why don't we say the whole volume there of this guy as is I'll tell you what. This is the length longwise, so we'll say it's 1/3 pi r squared, there it is, times the length. That's that x. That's the long one, all the way across. R1 okay, we got this. Okay. One almost looks like it's a one there. It's associated with him, okay? And the distance is, yeah, right. Then we just put an L there. Minus the small one. 1/3 pi. The small one is here, radius R2, and the distance there. Well, wait a minute. This is long distance. The other one's L. So I guess if we're talking about it, guys, you're talking about it. Here, this is L. This to here was the R1 over R1 minus R2 L. That's all of it. The difference between, you take the L away from here and you're set. Okay, well, isn't L the same as 1 over 1 times L, which is the same as R1 minus R2 over R1 minus R2? And take it away from there. All right. What happens is, if we're believing this, I'm just going, we're going on memory on this and saying what this thing's equal to when they actually do it. There's always an R, there's always an H, and I'll show you the way they actually do it in a second, but let's see what we got here. Let's go R1 over R1 minus R2 L minus L, and I got to get a common denominator, guys. How about R1 minus R2 over R1 minus R2? And it becomes R2 over R1 minus R2 times L. That's the short one. That's the short length. So that's going to be R2. Right. I mean, it's going to be R2 over the quantity R1 minus R2 times L. Okay. This is for the difference of two cylinders. Why is that important? Because this is from a difference of two cylinders. There's a real big cylinder, and you subtract the small cylinder, and you got what's left over. This is the big cylinder, I'm sorry, forgive me. This is the big cone. There's one big cone. There's one big cone right here. And subtract a small cone from it, and you got big cone minus small cone, you get this. Well, here's the big cone. Here's the small cone. And, even those thirds already are kind of putting a wrench into this thing. Like, how is it going to be, how does that even work? Yeah, it's certainly true. I mean, if you're talking about the volume of a cone, let's say let's say you started at 0, x equals 0, and you went out to here. This right here, this rise of r over a run from x equals 0 to x equals h, the slope is going to be r divided by h times x, and it started at 0. It started at 0 radius, so that's it. Y equals mx plus b. I get it, but the b is equal to 0. It's just mx. Y equals mx. Y equals, the y is going to be the r. And it just gets, and this is, look at this. It's a run of r and a rise, it's a run of h and a rise of r. A run of h and a rise of r. Wait a minute, what is that? R divided by h. That's how it's going to be behaving. It's going to be r divided by h times x. So how are you going to do this? R equals r over h times x, just to kind of verify it. Let's deal with it. Let's say it's pi r squared dx. I mean, it's pi r squared. Every cross-sectional area of the cone is area pi r squared times dx. You're going to integrate it from a run of 0 to h. Wait a minute, is there a way out of this thing? Yeah, there is. What it is, for the volume of the cone, it's going to be the integral from 0 to h pi. We said r over h. So it's going to be r over h times x. That's your radius. As x changes. From 0, no radius. Yeah, the cone is at a point. Is at a tip. I erased it, unfortunately. But r over h times x, or r over h times x, r over h times x, that's the radius, squared, dx. You're going to go from 0 to h. What do you got? We got pi is pi, r is a constant. Right here, r is a constant. It shouldn't, this is kind of, watch it. I mean, as we say here, it shouldn't even be r. It should be some function of r. Better way to say it, r of x. You know, the function of x. That's what I mean by r. So you got watch the symbols, guys. They're kind of redundant, I guess. The base area of this thing, yeah, that's r. That's h. They're constants. What goes on here, it varies. Cross-sectional area, I get it. But that whole length is a constant, some h. And this height is r, so it's r over h. What happens is, you end up getting pi constant. R meaning a constant now. It's not a variable. H squared, also a constant. x squared, not a constant, dx. Pi r squared over h squared. Integral from 0 to h of x squared dx. Yeah. There's your variable. Nobody else is a variable. It's right here. Pi r squared over h squared. Integrate this. Here's your 1/3. There's your 1/3. That's it. Well, you plug in an h right here. H cubed cancels with the h squared, just leaving you an h. It's 1/3 pi r squared h. 0, not a problem. It's 0. Indeed, it's true. Indeed, it's true. Well, yeah, it's true, all right. I'm just wondering if it's going to look anything like this. It's the same volume. It's got to be the same volume, because when you divide it by the same length, L, you should get this. It's going to be the same area at the end. Well, I'm going to get the volume. I'm going to divide the volume by L, and I should get the same average area, which is in that case, over there, pi R1, R2. All right, well, okay, we've said a lot. We're looking at a lot of this stuff, you guys. Yeah, I mean, it's sure saying a lot. Let's write it down, and let's see where it's going to go. We'll kind of conclude it and hopefully talk about a bunch of stuff that can help us out here, guys. All right, you look at this, you got what you got here. I don't know, the R2 goes over here, it's R cubed. The R2 goes over here, it's R2 cubed. R1 goes over here, it's R1 cubed. The bottom stuff and the other stuff, I mean, there's just a lot of stuff, man. Just trying to figure out what I want to say here. I guess you could say a whole lot here. You can say 1/3 pi. Let me just try to, let me just say this. 1/3 pi, and there's, you can argue this a whole bunch of ways here, how to put the 3 down there. I have the 3 in there too. There's a third every, there's an L in both places. There's a third in both, there's a third in both places, a pi in both places, an L in both places, and an R minus 1 in both places. So what we got here is pi, there's an L, there's an L in both places, and there's a third in both places, so there's pi L. There's a 1/3 in both places, there's a pi in both places, there's an L in both places, there's an R1 minus R2. That's big. R1 is big, R2 is small. These are all positive, not a problem. And you got the R1 cubed. Yeah, guaranteed positive answer. It's a whole lot here, man. Yeah, that is true. It's a difference of two squares. So if this is, so it's going to be, there's much you can do here for the volume. Difference of two squares here. So that right there, I mean, it's certainly verifiable. That's the closest to an R1, R2 I've seen. I mean, here, you got this. The R1, R2 that would be up there would cancel with this guy right here. Yeah, that's all great, but what's going on? I mean, got it looking like this. What's the average? What's the average area? Divided by L. Well, I mean, now you see it. You're looking at it, guys. I mean. Doesn't seem, there's your average area. Area, average, for that part of a cone. And here's the area average. Here's the average cross-sectional area. What does that mean? What that means is, if you multiply this average cross-sectional area by L, you'll get the volume of that truncated cone, of this thing right here. You'll get that volume. That's not the same volume as this average area, the pi R1, R2 multiplied by L. That right there, for cone, a truncated cone, C, let's say, and then for an ellipse, pi R1, R2. Perhaps, yeah, they could be equal at some. That's generally not an equation. That's generally not an equation. You think it would be? I'm dividing. If I'm dividing by the average area of this thing, what am I getting? What's that average area? We're thinking it's that. What's the volume? How does this whole thing work? I mean, you could even just say, well, look, I don't care about your cones. I mean, maybe the cones are the problem here. I'm just going to do a flat out integral. Go from here to here, and you let it, and let's see what it does. You're telling me, okay, you want to find the volume of that truncated cone, this part, but just go from R1 to R2, or go from 0 to L. Yeah, be my guest. It is the area, the cross-sectional area, and we're trying to find the average cross-sectional area. It's the area R2 minus R, when we're seeing how that work, R2 minus R1. I know that's negative. No big deal. No big deal. You'll see why. Divided by L times X plus R1. The whole thing, here, this is cross-sectional area. Yeah, I don't know what the average is. I got to do this, then divide by L, maybe find it, you know? How are you going to do it? Well, I mean, that's, you know, it's its own fascinating matter. I mean, but let me not beat it up too badly here, guys. You already kind of see the handwriting on the wall. It's not what you think it is. In general, you guys, even with the same stuff, the average of 1 over A as you're integrating. Remember, we integrated this thing like it was nobody's business. We made it it was dr equals rho dx over A. And whatever that was. The average of this is generally not the same as 1 over try to write it so you don't get confused. 1 over the average here. The average area put underneath 1 is generally not the same as the average of 1 over A. Try to put it another way, maybe. And that's kind of just, I just thought it was of interest. You weren't going to get away with it doing this. It's not the right answer. The right answer is this one. It's going to look like an ellipse, or at least behave like it is. That's the right answer. That's not that. Even for the same function. 1 over the area function. The average of that by the mean value theorem is generally not the same as 1 over the average of just A sub x. Okay, it was a little bit of a mess here, guys. If I were to get the average area and then put it underneath 1, that's not generally the same as the average of the function 1 over ax average. In other words, let me integrate 1 over ax. I mean, how do you get that average, actually? You know, if you were going to go between the limits of 0 to L, and you did 1 over the area function, dx. Let me just see here. Guys, I just run out of room a little bit. That's the answer. Now what does that mean? You've got it. You've got the feature on the film. You can go back. The average of the inverse of a function is generally not the same as 1 over the average of the function. If I were to take this function, integrate and divide by the interval over which I was integrating, I'd get the average of the function. 1 over the average of a function is generally not equal to the average of the inverse, the multiplicative inverse of a function. In other words, if I were to take a function, a of x, integrate it, divide by the interval over which I did the integration, I'd get the average of a of x. That would be, by the mean value theorem, I'd get the average of a of x. the average area put underneath 1. 1 divided by the average area is generally not the same as the average of 1 over AX while 1 over AX is integrated. So what are we talking about, guys? We've got this I won't erase any of it, but okay, so we could say basically, guys, for this right here, I'll try to, if you were taking the integral of, so let's what I just said, just ran out of room, guys. What I just said here, so if you were to take the integral from 0 to L, some L, let's stay with the language that they gave us. The integral from 0 to L of 1 over something. I mean, like in our, you know, some area function, let's say, with the pies and stuff like that. It's this whole thing that you're integrating. When you're done with that, you're going to divide by L, and you're going to get, basically what I was telling you, by the mean value theorem, you're going to get 1 over A of X, the average of that function. Now, if you take and you're going to get that. It's as simple as that. Is that the same as taking the average of period? So that's that. Is that the same as 1 over the integral from 0 to L A of X dx divided by L. And that would be that would be 1 over A of X, 1 over the average of A of X. Well, here's the stuff in red, here's the stuff in blue, and they're not equal. You know, generally they're not equal. I mean, when you look at, you're about to see it now. We're about to say, well, can I actually say here that the 1 over, you know, at the end of the day, the 1 over A, well, it's right here. There's an equivalent 1 over A here, which is 1 over pi R1 R2. Yeah, that's true. Not the same. That's not the same thing I concluded, though. When we had when we said, well, that's, we didn't conclude that to be the same thing as 1 over what I had earlier, the pi over 3. Pi over 3, we had the R1 squared minus R1, R2 along those lines. Remember, this is the area, that was the average area of this guy. That was the average cross-sectional area of this guy. That's clearly not that in a general sense. This is the average cross-sectional area of a elliptical cylinder with this constant cross-sectional area throughout the whole run of L. Throughout the whole run of L. So that's, it's a big thing in that regard. How we actually said it was going to play out, right? When we actually did that, right? We had that, we had the Q, they had the L's. Okay, we had a lot of stuff out there. We got rid of the L. Yeah, they're not the same. It's not working. This right here, fascinating, this right here is the average 1 over A. This right here is 1 over the average of the A. See, we're dealing with the same, in this case, we're dealing with the same mathematical object. The average of the reciprocals of the cross-sectional areas is 1 over the cross-sectional area of every cross-section of an elliptical cylinder. The average of the average cross-sectional area that I'm going to put right here, the pi R1, R2, yeah, I know, that's the A. 1 over A is equal to 1 over pi R1, R2. The average inverse area is 1 over the quantity pi R1, R2. 1 over the average cross-sectional area is this, and it doesn't work. So you would have been in trouble. True and true, but they're not equal. See what we got here. I mean, something like that. Yeah, it's 1 over. Right. This would be a volume. The bottom is a volume divided by a length. Oh, it's an area. It's the average area. Yeah, the average area, 1 over the average area, is this. For the same exact mathematical object whose average inverse areas is this. Average inverse areas is this, and 1 over the average area is this. For the same mathematical object, they're not equal. That's why they're not equal. That's why so this is true, and this is true, and let me just see what I could say. Just try to think here for just 1 second, as I want to look at it. Yeah, there's more to this. There's definitely more to this. But these, yeah, generally they're not going to be the way, and that's what I was trying to say earlier, guys. This 1 over AX, and you can do this, you can do other stuff with the mean value theorem to discuss this, or you can also, you can do this with discrete numbers too, and it doesn't work. Even with discrete numbers, it generally doesn't work, and with integrals, it doesn't work. It's another topic. We don't have to go there. 1 over, and then this is just the average on the bottom. So 1 over the average area is generally not equal to the average of 1 over the area function. The average of this function, which is the multiplicative, let's construct a function called 1 over ax. The average of this function, 1 over ax, a of x, not a times x, not a times x, but a of x. The average of the function, the average using the mean value integration and the mean value theorem, the average of the function a of x, the average of the function a of x is generally not equal to 1 over the average of the function ax. So the average, construct the function, the function's called what? 1 over a of x, that's your function. I want the average of 1 over, of this new function, we just constructed it. The function's called 1 over a of x, 1 over a of x. 1 over a of x is a function. The function 1 over a of x, that entire function 1 over a of x, what's its average? It is what it is. The average of 1 over, the average of the entire function 1 over a of x, we have an answer. And 1 over the average of a of x is another answer. Generally, they're not equal. That's kind of where they're going with that stuff, guys. When you actually, when you're doing this, just thought it was important to look at. I mean, it's how this whole thing plays out. Right. This is just the average of the function a of x. Get the reciprocal of the average of the function. Get the average of the function a of x and get its reciprocal. That's this. Get the average of this entire relatively complicated function, and that's that. And they're not equal. And there's so much more to be said on that, guys. But for our purposes right now, it's just something it's pretty important to look at. When you play through this thing, guys, it should come out the exact same way as it was coming out the other time, guys. If you're going to do something like this, how is this thing going to play out, and how do you actually get it? When you actually do this, you're getting the integral here with respect to x. You would do it. You'd have to this would be L over R2 minus R1, and you'd get, I'll show you in a second here. You can take the pi out of there too, and it's L over R2 minus R1 to do the integral. It's you make this like, this is your u, and then du dx would be this. Well, yeah, but you don't have it present, so put it there and then get the reciprocal. So this would be your function u, and then du dx would be this, and then you can just play it, leaving it like that. Well, let's actually do that, and then do that at the end of it. So what you have here, guys, you end up getting pi of this. When you finally get this done, you're going to get R2 minus R1, all this right here to the third. Here we go again. Here's that third. Again, I erased a lot of stuff, you guys, but I think you know where I'm going. And then we end up getting R2, R1 over L, X, R1 cubed. Here we go. 0, L. Pretty fascinating stuff, guys. More things change, the more they remain the same, it seems, right? Let's see what we got here. We got L right here. Bring the L in there. L's cancel. You got R2 minus R1 plus R1. That's R2 cubed. Put a 0 in here, and you got R1 cubed. R2 cubed, R1 cubed. Yeah, these cancel. You remember that. This is going to be, and of course I erased it, right? But this is going to be the quantity R2 minus R1 times the quantity R2 squared. I think there's supposed to be a plus there, guys. That was my mistake on that one. There should have been a plus there. So let's correct it now. This is the same exact conclusion I drew earlier, guys. Same exact conclusion I drew earlier. I just elaborated upon it a little incorrectly. This should have been R2 minus R1. They cancel. Then it would be R2 squared plus R1 R2. Shouldn't have been a minus. If I had a minus there, guys, I can't quite remember. Should have been this, and that would cancel. But that conclusion I drew is the same. I just coming to here. That still doesn't look like what I want it to look like. Fascinating. If it would have been, and then divide by L, and you got that. The 3 is kind of neat. Because if it's a circle, if it's completely a cylinder, symmetry throughout, if the R1 and the R2 are equal, this is R1 squared, this is R1 squared, this is R1 squared. 3R1 squared divided by 3 is R1 squared. Pi R1 squared, that's just one area times L, it would reduce to that. Notice if it wasn't a cylinder shape and if R1 and R2 were equal to just, R1 and R2 were equal to R, or they were equal to R1, let's call it R1. This is R1 squared, this is R1, so it's R1 squared, this is R1 squared. 3R1 squared divided by 3, R1 squared. Pi R1 squared times L, pi R squared L, that's if it was a cylinder, so it would work out. Okay? But it doesn't work, but again, what I told, yeah, as is right now, because of the disparity, it's, arguably pretty close. You could, if R1, if R1 R2 was equal to R2 squared and was also equal to R1 squared, then it'd be 3R1 R2. Divided by 3, it's R1 R2. Pi R1 R2 L, divide by L, you get the average area, which is pi R1 R2. Then you could argue it. But that's not going to be generally, you divide by L on each side, you're not able to say, guys, that looking at something like this, we're not able to say, definitively, even in this case, and so if you can't do it all the time, then it's generally not equal. It's just generally not going to be equal to, and this is what I was trying to, this is the average, this right here is the average of 1 over the A function. The average, not the average of the A function, not 1 over the average of the A function, the average of the entire function composed of 1 over A. The quantity 1 over A worked with the function 1 over A. What is the average of the entire function, the function called 1 over A? The average of the 1 over A function. This is the average. 1 over this is the average of the 1 over A function. This right here is R1 squared, R1, R2. No, I mean, I can give you some instances, if R1 and R2 are equal, I got pi r squared on the bottom, 1 over pi r squared. If R1 and R2 are equal and they equal R, let's call it some R, R1 equals R2 equals some R, 1 over pi r squared. This would be r squared. This would be r squared. That would be r squared. 3r squared times pi over 3 is pi r squared. It'd work. But in general, it wouldn't. And that's what I wanted to talk to you guys about. Okay. And that's pretty... And even in the discrete sense, you can see that with discrete numbers. You can play games with discrete numbers, not even in the continuous realm. You don't have to be using, calculus to do it. Say, wow, just even with discrete numbers, sometimes it might work, other times it won't. Generally, it's not true. In the most general sense, it's not always going to be true. So you can't say, oh, this is generally true. No, I cannot say that it's generally true. This is not generally true. Sometimes it is, but in general, it's not equal. In general, it's not true. In general, it's not true. All right. Thank you for your time, guys, and we'll talk. Take care. We'll talk again.